All right, good afternoon, everybody. How are you guys feeling? How's everybody feeling? I walked into this classroom thinking that this is going to be an awesome day and a great lecture, and I'm just getting like very low energy. How's everybody feeling today?
We just got our homework grades.
Yeah. Not so
Yeah,
good.
not
Oh,
great.
you got your homework grades? Are they not good in absolute terms or in terms of letter grade terms? This is after the outreach, Vijay.
What's that?
This is like after the outreach.
Right.
Okay. So what happened is we got the homeworks and I saw them and I said, Vijay, some people need some help. So give them an opportunity. Because some people just miss certain sections of the homework, like the comparative statics, for example. They just totally miss those. Yes, Brandon.
Is there somewhere where we can see,
The solutions?
yes.
Yes.
I just posted an
Oh,
MCG.
The solutions are posted. So don't freak out. Like you have another homework that you're working on now. And like honestly, like my desire in this class is if you work really hard, like for you to pass the class. So I hope that I've communicated that abundantly clearly. And just the fact that you're working in criminal, so you have an absolute grading scale, that should tell you that I'm really committed to that. I learned from one of your colleagues, Chris, that apparently there's like a distribution of grades online, so you can like look at me in the past. And how many of you guys have done that? I won't judge you. Okay, so you can see that like I'm not in the business of failing people from that, right? Is that true? Yeah. So I mean, like if you work really hard, like you are going to pass this class if you work hard. You will work hard, but you'll pass the class. So don't freak out about it. Okay. And then what I'm going to do, so the homework, the solutions are posted online, and I really tried. I was like, okay, some people just missed stuff, but Jade gave them an opportunity to do those things and get them back in the game. So I'm on your team, okay? What we will do too is for the midterm, so I'm going to give you an example of the midterm from last year, and you'll get that on Thursday. So after you've handed in your second homework, you can start like looking at that. I'm working on that, and on Tuesday, Majid is going to go over the solutions to that in class. You'll be able to ask questions and see that. I'll talk a bit more about that in class when I actually have it up. So I'm trying to think. And I'll be pretty clear in terms of like what the focus of the midterm will be. Because again, my goal is for you to succeed. I work pretty hard to teach, so it's sad if I feel like you're not learning, but I'm very happy if you're learning. Okay. So today, what were other questions or comments or commiserations? I think some of you guys did. It was hard, right? But you worked hard and you did decent. No. Okay. So today we're gonna continue with estimating returns from education using data. And then we're going to have a basic model of labor market signaling. Remember, I talked about this whole idea that the types of people that go to college will be very different to the types of people that don't go into college, right? Very simply, if Clemson sets a cutoff of, let's say, 1,000 for the SAT score, right? Then if you look at the earnings of somebody that went to Clemson versus the earnings of somebody that just only finished at high school, they're going to be different in terms of what their underlying SAT scores. So if you just ran a regression of wages on whether you went to Clemson or not, you're going to be picking up whatever human capital the Clemson graduates accumulated, but you're also going to be picking up the fact that at baseline, they had higher SAT scores. So even if they had not gone to Clemson, they were just kids that had a higher, that were better test takers to begin with, and maybe the labor market values that as well. And so we're going to talk a little bit about how education could actually be really valuable for folks, even if there's no human capital component. Basically, you can say, look, I'm a really high ability person. There's no way for me to signal that to the labor market. I'm going to go to college because it's relatively cheap for me to go to college because I can actually get into college. And that'll differentiate me from the person that can't get into college, even if all I do is just party, drink beer, and like go to football games. They'll say, oh, you went to college, right? Okay, good. And then we're going to hand back the homework, and then during the break, I have these flashcards here, and I'm going to hand these out during the break. I'd like for you to just write some reflections on the class, like just to provide feedback. What are some of the things that you like? What are some of the things that you'd like to see change, or some feedback from me? And the reason why I do this feedback periodically during the class is because I find that I want to be very responsive to you as students. my goal is for you to learn. Your goal is to learn too, right? And so let's just figure out what's the best way to make that happen. So in the past, I had a student who said, you were going too quickly through the lectures, or I wanted you to lengthen more to what we're gonna do next, or something like that. And that was really helpful for me because I slowed down a lot and made sure that I was checking to see if students were following in the class. And the students benefited, like everybody benefited from that comment. I benefited as a professor because what I would hate to see is that there's something about the course that you have a problem with, and then you struggle with that for the entire course, and at the end you give me a lousy evaluation because you didn't have a good experience, and then I have bad evaluations, and everybody loses, right? Instead, with these, you can say you're amazing in these ways. Here are some things that I'd like to see changed. Maybe there's nothing I'd like to see changed. Maybe I'm awesome when it comes to the course. That's fine too, like that. But I'll hand these out when we go on the break, and I'll get those two. So that's for this midterm evaluations. This is not like the midterm is today. Okay. All right. Other questions before we continue? No. Okay. Great. So I think this is going to be an awesome lecture. I just walked in with so much positive energy. I just spoke a little bit. Because today you're going to learn how to, like, what does it mean when we do some of these commands and data, like we have data, like how do you interpret that? I think this is such a super useful skill because when you go in the labor market, you're going to be able to say to folks, I actually know what I'm doing. That's huge. I had a student who got a data analytics job in Washington, D.C. He was able to show them a project that he did in his course. And so like, this stuff is super useful. Okay, so estimating returns schooling okay. So we have data on n people. This is the number of people. And what we observe are wages and years of school. And we're going to think about like a very simple stripped down model, but you can apply this to like other contexts where you add an experience, for example. So in the homework, you'll see that I ask you to look at interpreting coefficients of years of experience and actually thinking about how to calculate that. Okay. So we can turn this into the following interpretation, right? Let's define the log of wages for person I. Let's define that to be yi, so that we don't have like wages like floating around all the time. And then let's also define the log of wage zero. So this is the wages, the average wages if you did not have any years of schooling. Let's just define that to be alpha, just for simplicity. And with these definitions, our Mincer earnings function becomes yi is equal to alpha plus beta si plus epsilon I. Right? So again, this yi is what? This is the log of wages. This si is the years of schooling. So this is data. And this is also data too. And in these problems, it's really important to remember what is it that you observe and what it is that you don't observe. Okay? That's why I'm highlighting the fact that these guys are data. And in fact, we can be really fancy if we can actually box them. We're going to take it up to another level in the class. So this is data. remembers what this epsilon I is?
It's the error term that calculates everything that you're not taking into account.
Yeah, so this is our error term, or our residual. And so this is like all the stuff that we don't observe. So for example, we don't have experience in here. We don't have gender in there. We don't have race. We don't have what your major is. We don't have, to Brian's point from last class, whether you're a barista or an engineer or any of those other things that could actually influence focus. And so the goal of what we're going to do here is just to provide a very simple framework for thinking about how we can estimate these parameters alpha and beta. But this error residual is actually really important. Because if we observed everything that there was to observe about the person, then we can perfectly predict their wages. So this epsilon we can think of as being the predictive error. Okay? So what's the goal? So the goal is to use the data. And the data that we have is we have yi and we have si. Y equals 1 to n. This is just saying this. We want to use this data to estimate parameters alpha, beta. And I've called, so in the past I've used gamma here, so sometimes the Greek letters may change, but don't let that throw you off. The Greek letters don't have a permanent interpretation. It's just the interpretation you get by looking at whatever this function is and doing the exercise that we did last month. So don't let that throw you off, okay? Okay, great. Emily's with me. Yes, she is. Perfect. Okay, great. So this is the goal of what we want to do, right? So first, let me just throw this up on the board. We can visualize our data in the following way. Following graph. Right? We can have our earnings on the vertical axis. We can have years of schooling on the horizontal axis, right? And the reason why I specialize in the case of just earnings and schooling is because we can do this in 2 dimensions as opposed to having a third axis, right? Okay. Now let's say that we have the following data points. This is data point number 1, data point number 2, data point number 3, and let's see, data point number 4. Right? So these are 4 individuals, for example. Right? And we can put in some other data points too. Now, what we want to do is we've postulated this linear relationship between y and x. And so we want to figure out what's the right way to put a straight line through these data points. Right? And so let me put one such straight line through these data points. Let's say if I put the following straight line through these data points here. Do you like the straight line as a predictive relationship between earnings and wages? Why not? What's wrong with this in your mind? Huh?
It doesn't accurately represent the data.
It doesn't, right? Like none of the data points passes through this. Like every data point is completely mispredicted, right? What if I gave you this straight line here instead? Do you like that better? No? What about this one here? Do you like that better? Who prefers this line? Okay, who prefers this line? What about this line here? What is it about this line intuitively that appeals to you?
Follows the pattern of the data.
It follows the pattern of the data. Exactly, and so that's effectively what we're doing. So whenever you have data, you should be able to plot the data and look at what the pattern of the data is. And any relationship that you're going to predict from that should actually be used to explain the data. Because ultimately, when I get this alpha and this beta here, we're going to just get a straight line like this. And when we predict earnings, we're gonna say, okay, the predicted earnings for a given level of schooling, let's say this is, let's say for S2, if I say, what's the expected value of earnings for somebody who has S2 years of schooling, right? You're gonna go all the way up, you can go to this point here, you can say, this is my predicted value of the earnings, right? This is gonna be Y given SI equals 2. The expected value of Y given SI. And I'll put a hat over here. You've probably seen this in econometrics because this is predicted. Right? So this is the average or the expected relationship between years of schooling and earnings. Okay. Now, I'm going to erase these lines here that were bad lines. And I'm going to motivate how we're going to compute this relationship here, which I'm going to now put in solid blue. Okay. So for this line, we can go to any data point and we can look at what's the difference between the predicted value. What's the difference between the predicted value and the actual value? And that's going to be our epsilon residual that Brady was telling us about, right? Because for S1, you predict this amount of wages, but these are the actual reported wages that we have. And so this is going to be our residual epsilon 1. This here is going to be our residual epsilon 2, right? S3 is like right on the line. So epsilon 3 is just going to be 0, right? Epsilon 4 is going to be right here. And so for data point number 4, we're going to underpredict wages. For data point number 1, for person 1, we're going to overpredict wages. Now, our goal again is to estimate these parameters alpha and beta. And so in order to do this, what we're going to do is I'll go here. Okay. So we're going to proceed in a couple of steps. So the first step is going to be to write out this error residual. Because clearly this error residual is going to give us some information about how to do this. When we had this horizontal line here, the error residuals for everyone was huge, right? So if we had this horizontal line here, the error residual for 1 would actually be this. For 3, it would be this ginormous amount. For 4, it would be this ginormous amount too. So there's some relationship between these error residuals and how big it is. So to estimate parameters, the first step is for a given alpha and beta, write out the error residual. So we know that yi is equal to alpha plus beta si plus epsilon I. And so that's just going to imply that our error residual is going to be, what are the actual wages minus alpha plus beta si. Right? In principle, I should have hats over these because these are going to be the predicted hats. Okay. So if we take a given alpha hat, which is a guess at what this linear relationship should be, right? So we take an alpha hat. In this case, the alpha hat may be something like this, and then the beta hat would be 0 because this line is flat, right? So we take a given alpha hat and a given beta hat, and then we write down what the error is going to be, right? And so our residual is what the actual data minus what we predict. Okay. Step number 2, what we're going to do is we're going to compute the average value of the square of these residuals. that's gonna be the expected value of epsilon I squared, right? Epsilon I is residual. That's just gonna be 1 over n, the sum from I equals 1 to n of epsilon I squared, which is gonna be the same as 1 over n, the sum from I equals 1 to n of yi minus alpha I, minus alpha, sorry, hat, minus beta hat, si all squared. Let me pause there for a second. So we said, once we guess an alpha hat and a beta hat, which is a potential good line, then we compute these residuals. Now you may say, well, why are we taking the expected value of the sum of the square residuals as a measure of goodness effect? Why don't we just sum all the residuals, right? Because why wouldn't that be a great idea? Who has an answer to why summing the residuals might not be a good idea to assess goodness effect?
Because some values will be overestimated, some will be underestimated, so they would, because they'll be positive or negative, they'll cancel each other out.
That's exactly right. So if we just simply took that, so if we just took, and you guys are familiar with this technology, like when you do the expected value, some random variable, and that's the average. Who's seen that before? Has anybody not seen that? Okay, cool. So if we just took the expected value of epsilon I, we could have a poor fit even though the expected value of epsilon I is equal to 0. And this is because positive and negative residuals cancel. So let me give you an example of that. Let's say if we had this data, y and then s, and we had the points 1, 1 and 2, 2, right? We only have 2 points, right? And so clearly the line of best fit is going to be what? You just put a straight line between these two. There's no error. I predict this perfectly, right? So this is clearly the best line. However, if we were to draw this line here, this would have an expected value of epsilon I that's equal to what? We just drew a flat line that cut through at 3/4. This would be epsilon 1. Epsilon 1 would be equal to what in this case? It would be -1/2. What would epsilon 2 be here? What would epsilon 2 be here? Say it again? 1/2, right? Plus a half. So what's the expected value of epsilon I here? 0. What's the expected value of epsilon I for this line here, check? So an expected value of just the residual itself is 0 in both of these cases. But one of these lines is clearly better than the other. This line exactly predicts each point with absolute accuracy and the expected value of the errors is 0. This one has expected value of errors is 0, but that's because they exactly cancel out. And so this is why we use the expected value of the squared residuals and not just. Is everybody tracking with me so far? Question?
It's the blank of the residuals may cancel, what's that say? Because it says.
Oh, because the positive and the negative residuals may cancel. Sorry, thank you very much. Always good to ask those questions. Okay. Any questions on this? Chris, good? Randy? Yeah. Okay, great. So first step was we picked some alpha hat and some beta hat, right? And then we say, what's the residual here? And for any alpha hat and beta hat, we're going to get different residuals as we sweep through. Right? And now we compute the average of the square of these residuals. And we're going to take this as a measure of goodness of fit. What do we want to do with the square of those residuals? What do you think we want to do with those in order to pick the alpha and the beta that's going to give us the best fit? We want to minimize the square residuals. And why do we want to minimize them? Why don't we want to maximize them?
You want to have the line best fit.
Right, because if you minimize them, then in a sense, like on average, the absolute distance from this line is going to be smallest. The average absolute distance from this line is going to be smallest if you minimize them. Does that make sense? All right, great. Now I am going to optimization problem. Okay, I'm going to erase these two boards here. Everybody done with this? All right. So step 3, what we're going to do is we're going to minimize the sum of the square residuals, which is the same as maximizing the negative of that. Right? And when we, oh, okay. So let me write that out. Because there are like 2 steps. So let's go now. Step number 3. To choose line of best fit. We choose alpha hat and beta hat to minimize the expected value of epsilon I squared, the sum of the square residuals, right? And this is the same as maximizing minus the expected value of epsilon I squared. Right? So minimizing something is the same thing as maximizing the negative. Okay. And to figure out the maximum of this quantity here, with respect to these parameters, what should we do? What should be true at the maximum? And we've been doing this all semester. Say that again? The derivative of what with respect to what? Okay, so the derivative of the expected sum of the square residuals with respect to what should be 0. Hold on, what are we trying to find? What are we trying to find? No, what are we trying to find? What parameters are we trying to find? We're trying to find alpha and beta. And so in order, we want to find alpha and beta that minimizes minus the sum of the square, that maximizes minus the sum of the square residuals. So the derivative of this with respect to what should be equal to 0? That's right, alpha and beta, right? Does everybody see that? Because what we're changing is, we're choosing different lines. And whenever we choose a different line, we're changing alpha and beta. And so we're saying, as we sweep through all of the possible alphas and betas, how does that affect the sum of the square residuals, right? And so it should be the derivative of the sum of the square residuals with respect to alpha should be equal to 0. Add to max. These first order conditions should be true. And whenever we say first order conditions in economics, we just mean that there's something that we're trying to maximize, and we take the first derivative of it with respect to the parameter that we're solving for, or the endogenous quantity that we're solving for. That's all. So this should equal to 0, and also the derivative with respect to beta of minus the sum of the square residuals should equal to 0. Are there any questions about this so far? If you follow me, raise your hand. Say aye. Okay, awesome. I didn't see any hands in the back there. You guys good? Good job.
We're edging in the right direction.
Okay, you have a question?
No.
You good? Okay, perfect. I want to go through this in a methodical way because when you go to the homework, the example in the homework is more involved. So I want to make sure that you understand conceptually what's happening. The other thing too is I really want you to have a firm grip on like what we're doing here, right? Because otherwise, you can get into a situation where things seem a little bit murky. Okay. So, is that clock right in the back there? So it's five after?
Yes.
Okay, perfect. So we'll take a break, 10 minutes then. Okay, good. All right. So this is equation 1. This is equation 2. Okay. So now let's compute the derivative. In what? So we take the derivative of dd alpha of minus, so this expected value, the sum of the square residuals, we just take it from this equation here, right? So we can call it equation 0. So that's dd alpha of minus 1 over n, the sum from I equals 1 to n, of yi minus alpha, sorry, there's no I here, this is just constant, minus alpha, constant across the division, minus alpha minus beta si, and what do we put up here? Squared, right? That's equal to 0. Okay. Now when we take this derivative here, the derivative is a linear operator. And what we mean by that is we have a sum of terms. And so to take the derivative of sum of terms, we can take the derivative of each of the individual terms and sum them. Does that make sense? So we can rewrite this as minus 1 over n, and I'll go through this very slowly. The sum of I equals 1 to n of the derivative with respect to alpha. Now I'm going to put a big bracket here, and we're going to have a yi minus alpha minus beta si squared, right? Is equal to 0. Everybody with me, please.
Where's the negative 1 over n coming from? 'Cause
So this is, so we wanted to minimize the sum of the square residuals because a higher square residual is going to be a worse fit. And so that's the same as maximizing the negative of that. Yeah, it turns out that this negative sign is not going to matter because when we set this equal to 0, we just have a minus 1 multiplying this on the outside. And we can multiply both sides by minus 1, it doesn't matter. So this is more to be technically precise. Because I don't want you to write something down where you're maximizing the sum of the square residuals, because that doesn't make sense. Even, right? Okay. Any questions on how we got to here so far? Okay, right? So that's going to apply this, and that's going to apply that minus 1 over n, sum over I equals 1 to n. Now, we're taking the